Hello guys, welcome to my second lecture on doubly reinforced beam. So in the previous lecture I have explained the basic four steps for design of doubly reinforced beam. So in this lecture I'll be continuing with the same problem which I have listed in the previous video. So in this problem we have to design a simply supported beam of effective span 8 meter subjected to an imposed load of 35 kilonewton meter. Beam dimension are indicated in the figure below this figure. We have to use M20 Fe415. We have been given a beam of width 300 mm. The overall depth is 700 mm. So first step, we need to first list down the input details like we did in the singly reinforced beam. This input detail is not your design step but a preliminary step. So input details is your preliminary step. So I won't be writing anything, not preliminary anything. I'll be just noting down your input details. So input details section. If something is missing, then we need to assume for that that property. So input we have overall depth as 700 mm. We have width 300 mm. So what we required? We required the effective cover. So D dash we required. So for D dash we have assumed it as 70 mm. Let us assume this. Accordingly we will design. If the design is not safe, then we will reassume with some other value. So we have overall depth, we have width. So effective depth is your overall depth minus your effective cover. So this 700 minus 70 is your 630 mm. This is your effective depth. Please don't get confused between your effective depth and your clear depth, effective cover and your clear cover. So in previous lecture I have said if your effective cover is from center to your edge, this is your effective cover, and for clear cover is your edge of reinforcement. This is your clear cover. So there is a difference between effective cover and clear cover. Hope it is clear now. So we have effective depth. Now we have been given a UDL on your beam. This is UDL, simply supported beam. We have a UDL of 35 kilonewton meter. So simply supported beam, effective length, we have been given effective length as 8 meter. So the moment will be calculated as per this effective length. So now there are some dead load due to the size of the beam. So then next is we need to calculate the loads. So first is in the loading section, first is your dead load of beam, your beam section. So beam section is 0.3 meter, width, depth is 0.7 meter, and your beam density is 25 kilonewton per meter cube, which is equals to 5.25 kilonewton meter. This is considered for 1 meter of beam, 1 meter length. So this is 525 kilonewton. So there is additional UDL of 5.25 kilonewton meter. So the total UDL is total load is equals to your dead load plus imposed load. Imposed load is your 35 kilonewton. Your imposed load is your 35 kilonewton meter. Dead load is 5.25 plus 35, which is equals to 40.25 kilonewton meter. So now we have the total load. So we can easily calculate the bending moment for which we need to design the beam. So M, factored bending moment. For design we always need factored bending moment. So factored bending moment is your MU. So for simply supported condition, what is the formula? For simply supported beam, we have WL square by your effective length, 8. L is your effective length, and this is your formula W. So MU is equals to 1.5, that is your factor of safety. W is 40.25. L is 8, your effective length span square divided by 8. So this is your MU, that is your design moment. So 482.96 kilonewton meter. So for this moment we need to design this beam. So now we have to calculate XU max. Then similarly, like singly reinforced beam, we need to calculate XU max, which is equals to 0.48 D. D is your effective depth. 0.48 is for FE 415. This I have been explaining in every lecture. So 0.48 into 630. We have assumed a effective cover of 70 mm. So which is equals to 302.4 mm. XU max is 302.4 mm. Now comes the design steps. 4 design steps. These are your input calculations. Now is your design step 1. This was your preliminary step, which is not included in your design step. So step 1 is determination of MU limiting and AST limiting. MU limiting and AST limiting. So MU limiting, we have formula. MU limiting is equals to 0.36 XU max by D1 minus 0.42 XU max upon D BD square FCK into BD square due to this restriction in width. You can put this FCK BD square. So which is equals to 0.36 XU max is 302.4. D is nothing but 630 1 minus 0.42, then 302.4, 630. FCK is 20, BD square, B is 300, D square is 630 square. So 630 cancel. So which is equals to 328.55 kilonewton meter. So AST limiting is as per your MU limiting. So AST limiting is equals to MU limiting, AST limiting, MU limiting upon The point AST limiting is your mu limiting by 0.87 Fy d 0.42 xu max, which is equals to I'll directly write down the value of AST limiting. You just need to put all the values and calculate. Since we have to make this video short and simple, I'll just write down. This is a simple calculation, so I don't need to repeat the step. So AST limiting we have calculated. Now step 2. Step 2. In the step 2 we need to calculate, determine mu2. Determine mu2. Mu2 is your difference between mu and mu limiting. Mu2 and ASC, AST2 and AST. So first we will directly calculate mu2. Mu2 is nothing but your mu minus mu limiting. So mu is 482. We have already calculated the preliminary step. Then your mu limiting we have calculated step number 1, which is equals to 154. So this is the additional moment for which we need to design doubly reinforced beam, for which the doubly reinforced beam requirement has come. So mu2 is calculated. We have for calculation of ASC we need to calculate FSC. For FSC we have a table, so where we need to calculate the ratio d dash by d. So d is 70, this is 630. D dash is 70, and d is 630. So which is equals to 0.11. So from we have a table. The table is present in IS 456. So I'll directly show you the table from where we will calculate we will find the value of FSC. So we have d by d dash. Our d dash value is 0.11. So we have 415 grade steel. So 415 point, we have to interpolate between 0.11 and 0.15. So it will come nearby 53, 353. It will be somewhat near to 354 point something. So using that table you can find FSC. So FSC by interpolation will get 350. Let us check. We have 0.11 and 0.42, the difference between 0.53 and 42. So by linear interpolation we can find the value of FSC, which is equals to 350.8 Newton per mm square. Please find this value by linear interpolation in that table, from that table interpolation. So we have FSC. So ASC is equals to mu2 upon FSC minus FCC. FSC is your stress of concrete, and this is your d minus d dash, which is equals to we have all this formula. We have this for FSC, use 0.446 FCK. This is your FSC value. So 0.446 FCK. So I'm not calculating everything, I'm just writing I've already calculated this ASC, so I'll just write the area of steel. You can use mu2 here, you can use FSC, which we have calculated here. FC says 0.446 FCK, D is your 630, D dash is 70, so which is equals to 806.517 mm square. So AST2, we have to find AST2 also. So AST2 is ASC FSC minus FCC upon 0.87 Fy. So we have FCC here, FSC here, FSC here. So Fy is 415. So we can directly calculate. I'm not calculating. I'm not writing the values. I'm directly calculating it. So to calculate, so we have this formula for AST2. AST2 is AC, FSC. FSC we have already calculated from the table. FCC is 0.446, FCK 0.87, FI is equals to 763. You can calculate. I'm not calculating. I'm already calculated, so I'm just writing the value. You can verify 6934 square. So AST, so total AST is equals to AST1 plus AST2. So which is equals to we have calculated AST1, which is your AST limiting. AST limiting was your AST1. AST limiting was your AST1. So AST limiting was 1809.14 plus AST2 is 763. 694, which is equals to, so let's calculate this. 763.763. I'll use a calculator because I have not calculated this. 1809.14 plus 763.694 is equals to 2572.83. is equals to 2572.834 mm square. So this was our fourth. This was our third, for the second step. So step number 3. Step 3. Step 3, we need to check maximum and minimum, maximum and minimum and maximum, minimum and maximum reinforcement in tension and compression. Tension and compression. So minimum ASC is equals to 0.2 by 100, 0.2%. So which is nothing but this is your B, this is your D, which is equals to 4. So we have maximum ASC maximum is equals to 4%. So 4 by 100 into 3 is 700, which is equals to 800,400 mm square. So thus our reinforcement, which was 806 for ASC, we have calculated 806 for ASC, 806 for ASC, so which is 420, 806, 517, which is less than 8400 mm square. Hence, okay, this was for compression. Similarly, in tension, the previous one was for compression. In tension, AST is equals to 0.85 BD by FY. This was your minimum, so which is equals to point, not point, it is 387.1. These values we already have, so I've just directly written the value. AST maximum AST, which is equals to 4% to B into D. B into, here it is your capital D. Everywhere is your capital D, not small d. 700, which is equals to 8400. So area of ceiling reinforced. So total AST was 2500 2572.834, which is greater than 387.1 and less than 8400. Hence, okay. So now we are into our fourth step. Last step, step number 4, where we need to identify the a number and dia of bar. So for ASC, we have assumed, directly write, we have assumed two numbers 20 tor bar, that is 20 dia bar, plus two numbers of 12 dia bar, which is equals to, we have 628 for 20 and 226 for this, the area of this, which is equals to 854, which is greater than required. So okay. And second is here AST. So AST same, 4 numbers of 25 dia plus 2 numbers of 20 dia. So this area for this is 1963 and this is 628, which is equals to 2591, which is greater than 2572.834. Hence, okay. So this was the problem where we have designed seeing doubly reinforced beam. Each and every step was clearly mm, clearly calculated, clearly explained. So hope you have understood this problem. If you have any query, you can comment. We will try to answer your comment. So have a great day and hope you understood this problem. We will come up with few more lectures. Till then, take care, bye, and please subscribe to my channel. Thank you.